Hello everyone, this is Ruai PCB, your trusted PCB partner. Today our topic is crosstalk control in four-layer PCBs, the definition, hazards and mechanisms of signal crosstalk. In the intricate world of high-speed PCB design, we frequently encounter a particularly tricky and pervasive problem, signal crosstalk. It exists much like an elusive ghost, silently and insidiously affecting the overall signal quality and often leading to significant system failures. Today, we will thoroughly delve into the precise definition of signal crosstalk, explore its various detrimental hazards, and meticulously examine exactly how this phenomenon is generated within the complex layers of a printed circuit board. This is a demonstration PCB we looked at earlier. There are many traces here and the spacing is very tight. However, most of them use differential pairs, so crosstalk is not very severe. If single-ended traces were used, the crosstalk would be much more noticeable. So what exactly is signal crosstalk and just how harmful can it be? First, the definition of crosstalk refers to the phenomenon where, when the current or voltage on one signal line changes, electromagnetic coupling, mainly capacitive and inductive coupling, induces unwanted voltage or current on adjacent nearby signal line. Usually, we refer to the signal line generating the crosstalk as the aggressor line and the line affected by the crosstalk as the victim line. So, what are the dangers of crosstalk? The first is that it causes signal distortion. Crosstalk gets superimposed onto the normal signal of the victim line, altering its waveform and resulting in overshoot, undershoot, or ringing, which seriously affects signal integrity. The second is false triggering. Crosstalk may cause the voltage on the victim line to reach or exceed the threshold of the logic gate, resulting in the receiver misjudging the signal state, which leads to false triggering or data errors. The third is system instability. Severe crosstalk can cause the entire system to malfunction or even crash. The fourth is that it makes debugging difficult. Crosstalk issues are often hidden and hard to pinpoint, posing significant challenges for debugging. Let's take a look at crosstalk. The line on the right carries a signal which generates some electromagnetic signals that affect the line on the left. The line on the right is called the aggressor line, while the one on the left is called the victim line. It transmits through this parasitic capacitance, CINM. In fact, parasitic capacitance and parasitic inductance are not actual components, but rather are formed inherently. Through these parasitic capacitances and inductances, the signal is induced onto the victim line, causing changes in the waveform of the victim line. So, what is the mechanism behind the generation of crosstalk? It mainly comes down to capacitive coupling and inductive coupling. The essence of crosstalk is the transfer of electromagnetic field energy between adjacent conductors. First of all, capacitive coupling occurs when the voltage on the aggressor line changes. Through the parasitic capacitance between the aggressor and victim lines, part of the changing electric field energy is coupled onto the signal line, generating an induced voltage. You can imagine it like two water pipes placed very close together. If the water pressure in one pipe suddenly changes, the deformation of the pipe wall will affect the water pressure in the other pipe. In this illustration, we can see that if there is a parasitic capacitance here, then the high frequency signal on the aggressor line will be capacitively coupled and induce a signal onto the victim line. Because a capacitor blocks direct current but allows alternating current to pass, high frequency signals can easily pass through this parasitic capacitance. Next, for inductive coupling, when the voltage on the aggressor line changes, it generates a changing magnetic field. This changing magnetic field passes through the victim line and its return path, forming a loop and induces a counter electromotive force on the victim line, generating an induced current. This is what we call inductive coupling. That is, the parasitic inductance on this line. When current flows through this inductor, it inevitably generates a magnetic field with loops of magnetic flux, and this magnetic field will extend to the victim line. Then the magnetic field on the victim line, through the parasitic inductance on the victim line, generates a counter electromotive force, forming a loop on the victim line. Furthermore, in actual PCB routing, both capacitive coupling and inductive coupling coexist and work together to produce the result. It's not the case that we only have capacitive coupling or only inductive coupling. They exist simultaneously and together determine the magnitude and characteristics of crosstalk. An introduction to crosstalk and signal layer layout. The magnitude of crosstalk is related to multiple factors, among which the spatial layout of signal lines is crucial. First, the first factor. Second, the parallel length. The longer the parallel routing between the aggressor and victim lines, the more severe the crosstalk. This is easy to understand. The longer the distance between the two, the more time and space there is for crosstalk to occur between them, so the impact becomes more significant. Therefore, we generally do not recommend long distance routing next to strong signal lines. The closer, the better. Next, line spacing. The smaller the spacing between lines, the stronger the coupling and the more severe the crosstalk. As we can see on the left, the line spacing is 3 times the line width. So it is generally recommended that the spacing between traces be 3 times the line width for optimal results. On the right, the spacing is less than 1 line width, which results in very serious crosstalk. Such dense routing is not recommended unless there are special circumstances and there is really no other option. Normally, it is recommended to widen the spacing between traces as much as possible. You can also control the line spacing by setting rules and routing specifications. Alright, the third point regarding signals is the signal rise and fall time. The faster the signal transitions, the more severe the crosstalk, because the electromagnetic field changes more dramatically. This is why we do not recommend routing traces under components like crystal oscillators or under their signal lines to prevent this kind of crosstalk. The fourth point is the reference plane. A complete reference plane adjacent to the signal line can effectively absorb part of the electromagnetic energy and reduce crosstalk. This is why, on a 4-layer board, we designate the 2 inner layers as ground and power, respectively. The main purpose is to use a complete plane to absorb part of the electromagnetic energy and reduce crosstalk. Interlayer coupling. In multi-layer boards, there is also coupling between adjacent signal layers, which leads us to the next topic, interlayer crosstalk, which we will explore in depth. Today we've gained an initial understanding of signal crosstalk, learned about its hazards, and the 2 mechanisms by which it occurs, resistive coupling and inductive coupling. We've also learned that crosstalk is closely related to the spatial layout of signal lines. In the next video, we'll focus on interlayer crosstalk specific to 4-layer boards and learn how to control it by optimizing layer order and using shielding technique. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.